Welcome everyone. Today with us we have Martina. Martina now is a postdoc in the CISA MATLAB group, and today she will talk about her latest research field, so linear stability and transient behavior of viscoelastic fluids in boundary layers. Thank you, Martina.
Thank you for the introduction, Maria. So hi everyone. As Maria said, today I will talk about my PhD research. But first of all, I want to say a little bit about me. So I started recently working with your group. I started the 1st of February, and I will be working in collaboration with the JRC. I am from Vicenza. I did my bachelor degree in applied maths in Verona. My thesis was about the pricing of Asian options using numerical methods. Then I moved to Milan for a master degree in maths, which was focused on applied subjects and numerical analysis. My thesis was focusing on the virtual element method combined with domain decomposition. After the master, I did a brief experience in industry and worked for an IT consulting firm, always in Milan. After that, I did a PhD at Cardiff University, and I was supervised by Chris Davis and Tim Phillips. I actually included a map of the United Kingdom just to show you where Cardiff is on the map. Cardiff is the capital of Wales, which is not in England, but is part of the UK. So, today I want to give you an introduction to the research I did during my PhD. So the aim of my research was to understand the stability behavior, so understand how disturbances grow or decays and in what ways, of viscoelastic fluids, which are examples of non-Newtonian fluids. Non-Newtonian fluids are very common in nature and in industry. For example, blood, paint, toothpaste, and many others are non-Newtonian fluids. Specifically, viscoelastic fluids exhibit both viscous and elastic properties. A very important feature of viscoelastic fluids is the presence of non-zero normal stress differences, which are responsible for very interesting phenomena. For example, the Varus Effect and the Weissenberg effect. So we can observe on the left the Varus Effect. So we have a viscoelastic fluid which is extruded from a tube, and we observe a considerable swelling of the diameter at the extrusion. On the right instead, we have another very interesting phenomena, and I found it actually very cool. So we have a beaker filled with a viscoelastic fluid, specifically a polymeric fluid. We observe that when we rotate a rod inside this beaker, we observe the fluid climbing up the rod. And notice that for Newtonian fluids, we would observe the opposite behavior. Newtonian fluids will actually move towards the boundary instead. So we focus on boundary layers, which are thin layers of fluids next to a rigid wall, next to a surface. And specifically, we consider a wedge placed symmetrically with the flow direction. Right, so as an example of a viscoelastic fluid, we choose a second order model for the Cauchy stress tensor. Second order fluids are part of a bigger family of fluids called order models, which was proposed by Rivling and Eriksson. So the constitutive equation for this model consists of a part which is the Newtonian law, which is the blue part here, plus some additional terms which account for non-zero normal stress differences. I will tell you a bit more later about that, about what I mean by non-zero normal stress differences. So alpha 1 and alpha 2 are the normal stress moduli, and thanks to this relation, we will be able to consider only alpha 1 in this talk. A1 and A2 are the Rivlin-Eriksson tensors of order 1 and 2. A1 specifically is the rate of strain. A2 is a convective derivative in time of A1. Then also we have the balance of linear momentum and the continuity equation under constriction of incompressibility. Right. So for this model, we will consider both signs of alpha 1. The reason is that for alpha 1 positive, this model is compatible with thermodynamics. But for alpha 1 to be negative, it can actually predict the correct sign of the normal stress differences. And also, this constitutive equation for alpha 1 negative was found to correctly approximate the stability results of more, let's say, more complex viscoelastic fluids. So I want you to focus more on the case of alpha 1 to be negative from now on. Right, in order to understand better what are the main non-Newtonian features of this model, let's see how this behaves in a very simple configuration. So we consider a steady, simple shear flow of this type. And for this flow, we can calculate the components of the extra stress tensor and define the viscometric functions. So the viscometric functions are eta, which is called the shear viscosity. N1 and N2 are the first and second normal stress differences. So from here, we can see that eta will be constant. So this model will not predict any shear thickening or shear thinning behavior. So the viscosity will be constant, as for Newtonian fluids. Instead, for alpha 1 negative, as I mentioned before, N1, the first normal stress difference, will be positive. It has been found in experiments that N1 should be positive and N2 should be very small compared to N1. Right. As I said, we want to understand the stability characteristics. But in order to do so, we need to determine first the mean flow, so the flow which is undisturbed inside the boundary layer. In order to do so, we apply a boundary layer theory, which is very similar to the boundary layer theory applied for Newtonian fluids. And one reason to consider this second order model is that it's actually possible to apply such a theory. So the basic idea is that the thickness of the boundary layer is very small compared to a chosen characteristic length. This can be ensured if considering very high Reynolds numbers. But also, for this model, we also need a non-Newtonian parameter, which I will introduce in a bit, to be very small. So applying these assumptions allows us to simplify the equations and then to apply a similarity transformation, where now eta is the boundary layer variable. Then the mean flow will be found by solving this ODE. Here, K0 is the is the non-Newtonian parameter, which is based on the displacement thickness at a certain distance from the leading edge. So K1, K0 is proportional to alpha 1, which is the material moduli which appeared in the constitutive equation for the second order model. Another thing to say here is that M is a parameter which is related to beta H, which is the angle parameter, which tells us essentially how wide the wedge is. So we couple this equation with boundary conditions, which are here to ensure to have a zero velocity at the wall and to match the external velocity far from the wall. Notice that for the second order model, we have additional terms, and the equation is an order higher than Newtonian case, so we need an additional boundary condition. So for the sake of the stability analysis, we assume the flow to be parallel, and this is possible because we are considering very high Reynolds numbers. So the first step, so I want to talk about a little bit about the linear stability analysis and the equations. But for this, I want to restrict to the two-dimensional case for simplicity. So as we said, we have a parallel base flow, and we assume, because we are in the linear case, the disturbances to be very small, so infinitesimal and wave-like. So here, phi is the string function, alpha is the wave number in the stringwise direction, and omega is the frequency. So, right, assuming wave-like disturbances allows us to find the so-called Sommerfeld equation, but with an additional term due to non-Newtonian effects. So again, UB is the mean flow, so the flow which is undisturbed. Phi is the disturbance profile. Rho is the Reynolds number based on the displacement thickness. K0 is again the non-Newtonian parameter. So we focus the attention on the temporal problem. So we want to see how the disturbances grow or decay in time. To do so, we keep alpha real and fixed, and we solve this equation for C. Essentially, if C has a positive imaginary part, the flow will be unstable and the disturbances will grow exponentially in time. And if C has a negative imaginary part, we will have a stable flow, and the disturbances will decay exponentially in time. So I will present first the two-dimensional results. So here are the temporal growth rates for two different values of the angle parameter. So, right, the case on the left, we have a wedge, and we compare Newtonian and non-Newtonian temporal growth rates. We can see that for a negative K, we have an increase of temporal growth rates. So the flow become more unstable. Instead, for K positive, the flow become more stable. And the same behavior, qualitatively same behavior, is found for a stagnation flow. So when beta is 1. Right, some more two-dimensional results. So we present here neutral stability curves, which are regions that separate stability and instability on the plane. So essentially inside the curves, the disturbances grow exponentially in time. Outside the curves, we have a stable flow, so the disturbances decay. So we can see that K negative, which was found before to increase the temporal growth rates, has a destabilizing effect because it increased the region of instability. Instead, K positive will decrease the region of instability, delaying then the onset of instabilities. Right. Next, we need to consider also three-dimensional evolution of disturbances. The reason is that for Newtonian fluids, there is a theorem called Square's theorem, which allows us to reduce the study to two-dimensional disturbances. But such a theorem is not valid in general for any kind of fluid. And in particular for this model, it cannot be proven. So I know that it has been proven only for very few viscoelastic models. So what we need to do is to, again, consider a normal mode form for the one normal velocity and the vorticity. But in this time, we consider also the span-wise direction, which is denoted by Z, and beta here denotes the span-wise wave number. I don't want to go into details and show you the equations, but show you directly the results. So, for example, we consider the case of a flat plate. And we see that we have a very interesting behavior. So if we focus on this plot over here, where alpha is very small, so we are in the case of of waves that are almost independent of the streamwise direction. So they are mainly directed in the span-wise direction. So here we found that K negative is found to reduce the growth rates for this kind of waves, and the opposite for K positive. So the non-Newtonian terms act differently for waves that are mainly directed in the stringwise direction and waves that are mainly directed in the span-wise direction. And I found this actually very interesting. So in the next section, I want to consider something that is called the bypass transition. So in systems that are dominated by shear forces, such as boundary layers and channel flows, it's very important to consider a no-model approach as well. So in classical linear stability analysis, we study the eigenvalues of the stability operator, as we have done so far. But if this stability operator is non-normal, then eigenvalues can be misleading. So we need to consider also a no-model approach, which allows us to study how disturbances behave in shorter period of times. So in the first figure, we have a flow over a flat plate, and we see that by increasing the Reynolds number, the flow becomes unstable. So we observe that the flow becomes unstable due to variation in the streamwise direction first, and then only later, three-dimensional effects are triggered. This kind of transition scenario is very common in low noise environments. And this scenario is captured by applying the classical theory based on eigenvalues that we've seen so far. However, sometimes we see this kind of behavior. So we have the presence of streamwise vortices, which are then transform into stringwise streaks, which are regions of high and low velocity in the stringwise direction. This kind of transition to turbulence cannot be explained by the modal theory. That's why we need to consider also bypass transition. So, right, what is bypass transition? Is the transition emanating from no-modal growth mechanisms. It is due to the non-normalities of the stability operators. So essentially, we see that even if all the eigenvalues of the system decay, we can still have growth of energy for smaller period of times. The main mechanism for instability is called the lift-up effect or vortex tilting, which is the conversion from stringwise vortices to stringwise streaks. So the traditional analysis holds only asymptotically, so for the time that goes to infinity. But in experiment, it has been observed for shear flows that are subcritical transition to turbulence. So turbulence happening at lower Reynolds number than the ones predicted from the classical analysis, stability analysis. Always in experiments, we observe vortices and streaks. So in the past, a lot of work has been done for Newtonian fluids in this topic. A little bit of work has been done for non-Newtonian fluids, but mainly in for channel flows. That's why we want to expand this. We wanted to expand the study to boundary layers. So the starting point is an initial value problem. So again, it's a linear analysis. So we linearize and we assume wave-like disturbances, but this time we retain the dependency on time so that we can see the time evolution for shorter period of times. And we rewrite the stability equations as an initial value problem. I will not go into details of the specific operators. Right. In order to quantify the transient behavior, we define the maximum possible amplification, which represents the maximum possible amplification of energy density over all possible initial configurations. So G eventually is a curve, when we fix alpha and beta, is a curve changing on, depending on time, which is the envelope of all the possible evolutions of energy. So again, we always compare Newtonian and non-Newtonian results. And we see that for K negative, we have a decrease of the transient growth, while for K positive, we have an increase of the transient growth. Next, we calculate the maximum overall time, and we represent this in a alpha beta plane. Just as a reminder, alpha is the span-wise, string-wise wave number, beta is the span-wise wave number. Observe that for the Newtonian case, so when K is 0, the maximum happens for alpha equals 0. So the kind of disturbances which gain more energy are the ones that are stringwise independent and takes form of stringwise vortices. So for the non-Newtonian case, for second order fluids, we observe that that is the same, that the maximum is also obtained for stringwise independent waves. And we observe that for K positive, we have an increase of transient growth, while for a K negative, we have a decrease of transient growth. So we show here optimal disturbances, which are the initial configurations that gain more energy. Right. The choice of the parameters here means that we are along this line, so we are very close to the maximum. So we can see here that the optimal disturbance take the forms of stringwise vortices, which are then converted to very high velocity in the stringwise direction. And this is the so-called lift-up effect that I mentioned before. Right, what we did later was to run some DNS in order to confirm the results that we obtained so far. So in order to do so, we write the governing equations in a so-called velocity vorticity formulation, which is derived by applying the curve to the governing equations. So the governing equations are written in terms of two perturbation vorticity components and one velocity component. So I don't want to go into details of these equations, but just notice that for the non-Newtonian case, we have many more terms which complicate the formulation. So what we did was to verify that this formulation is equivalent to the full version for second order fluids. We solved then, we imposed a temporally localized impulse, and we solved the equations using a Chebyshev-Tau method. An important role is played by a mapping from the semi-infinite domain to a finite domain. The mapping is very important because it's how it's important in making sure that the boundary conditions are satisfied. So just as an example of what we use this simulation for, so as I said, we apply a temporally localized impulse, and we calculate the temporal growth rates. We compare the temporal growth rates obtained using the simulations and the temporal growth rates calculating using the eigenvalue problem. And we see that actually the two solutions match very well. So I only want to say a little bit about a preliminary work that we did for more complex viscoelastic models. So we choose the upper convected Maxwell Oroyd B linear Pantini-Tanner and exponential Pantini-Tanner and Gizicus models. We wrote them in a single constitutive equation in order to study them in a more compact way. So, so the main challenge is to determine the mean flow of these fluids in the boundary layer. So in order to do so, we applied an asymptotic suction boundary layer. So we assume a uniform suction at the wall, and this allows us to simplify the equations considerably. So for Newtonian fluids, this means that we can obtain an analytical solution. So we found that also for two of the models, the upper convective Maxwell and the Oroyd B models, we can find analytical solutions in the boundary layer. and a very simplified version of the equations for the remaining models, which we solved numerically. So the next natural step would be to use this starting point to apply a linear stability analysis, similar to the one that we applied for second order models. So in summary, we applied a classical linear stability analysis based on eigenvalues for second order models. We considered both two-dimensional and three-dimensional disturbances. We studied both the temporal and spatial evolution of disturbances, although I didn't present the spatial results in this talk. We extended the analysis to consider also a no-model approach for second order fluids. We ran DNS to confirm the linear stability results. And we also did some preliminary work on more complex viscoelastic models. Okay, if you have any question, I will be happy to answer.
Thank you, Martina, for the talk. So guys, if you want to make a question, you can unmute yourself directly. Let's wait a little bit. Let's see if someone has a question.
Sure.
Okay, maybe I can start with some questions. First of all, I mean, my question is about the model itself. The first thing that you said is basically that you have this length that is higher with respect to the boundary layer problem, right? I mean, the length, yes, the characteristic length is much more larger with respect to the problem, and also K is not high, right?
Yes.
I mean, my question is, this is an assumption in order to, in a sense, make everything work fine with, I don't know, simulations and so on, or it doesn't make sense to ask questions about boundary layers and stable and unstable stuff if these parameters change?
Well, so if K to be very small, it's important to have a valid boundary layer theory.
Okay.
But it's also the kind of problem that we are studying. So we are studying very dilute polymer solutions. So let's say that the non-Newtonian effects are very small.
Mm-hmm.
Yeah, so yeah, it makes sense for the purpose of applying a boundary layer theory, but also because we want to consider very diluted polymer solutions.
Okay, so like with small effect of this strange type, like, I don't know, the fact that, you know, the fluid does not go down when it pours or something like that.
Yeah, we don't see very dramatic effects like the one that I showed here.
Okay.
But well, one motivation to study these very dilute solutions is that they found that in turbulent regimes, even a small addition of polymers is found to decrease the drag.
Okay.
So, yeah, so.
Okay, so the motivation actually is turbulence and see how dilute stuff actually could help in this sense. Okay, yes. I see. And so now I have another question. The parameters that you showed us, like alpha and beta, about the waves stuff, I saw that basically the range of the parameters are somehow fixed. I don't know if I lose it in the presentation or you can
like
explain, explain a little bit about, I don't know, alpha is always less than, I think, something like 0.6. I never saw something an alpha higher, and also beta, it's always like from 0 to 1. So if you can explain a little bit these parameters.
So, right. Well, for example, here, alpha, we choose this range of alpha because that's where we find the unstable region, right?
Okay.
But also, alpha is the wave number. This means that it's periodic, so it makes sense to study only.
Okay, so an interval, and then everything repeats. Okay.
Yes.
Okay. I see. And I have a last question. Sorry, but it's later in the transient part of the bypass transition, because you actually, in order to study this bypass transition, you, correct me if I'm wrong, you have this sort of energy capture stuff like G equal to the maximum of the Q. Okay, so I lost what Q is actually. It's my bad. And the other question is like, this is, I think, a standard energy. Are there other energies that you can somehow
this is the kinetic energy density norm.
Okay, so it's like a standard thing. Okay.
Yeah, Q essentially is the solution of this initial value problem, which I didn't go into details, but is obtained by an eigenvalue decomposition.
Okay.
Solving this problem here.
Okay, I see. Okay. Are there other questions for Martina? Once again, you can unmute yourself, guys, if you want.
I know the topic is very different.
Yes, it's a bit different from, yes, our background, but still it can be useful. So it seems to me that, no, yes, no, I don't know if Martin maybe was, no. Okay, it was a mistake. So Martina, I thank you again for your talk.
Thank you.
And guys, we see.
Yeah, I only wanted to say one more thing. So if anyone has any interest in non-Newtonian fluids or viscoelastic fluids, I'm happy to discuss.
Yes.
Because although I will be doing more like numerical stuff, so I'm still interested in these kind of topics as well.
Yes.
Thank
yes,
you.
I mean, you know Martina. I mean, the people from the group know Martina from other group meetings and so on, and other people can contact her. I think it's fine. Thank you very much, Martina, for the talk. Guys, let's see each other for, I mean, the following AJS next Friday. Thank you.
Thank you.